And now let's talk about the gradient descent, which is the topic 11. Gradient first is the main method. Gradient descent is an iterative optimization method that minimizes functions by updating parameters in the opposite direction of the gradient. Think of it. It's like going downhill. At each step, we follow the steepest descent direction. And the gradient vector, which is this, points in the direction of the fastest increase. So we move against it to find minimum. And then maybe let's look at the code here. Well, first let's examine our basic gradient descent implementation. The core update rule is simple, which is this part, where alpha is the learning rate controlling step size. In Julia, we use automatic differentiation and vectorization for efficient computation. Our code shows this clean implementation with trajectory tracking to visualize the optimization path. And now for the learning rate effect demonstration here. Now let's observe how learning rate choice dramatically affect performance. With alpha equal to 0.1, we get smooth convergence. But with alpha equal to 1.1, we see dangerous oscillation. The algorithm overshoots and bounces around the minimum. Conversely, alpha equal to 0.01 causes painfully slow convergence. This demonstrates why learning rate tuning is crucial in practical. And then let's talk about the problem and limitation. Well, the basic gradient descent has significant limitations. It's sensitive to learning rates and can get stuck in local optima. More critically, it struggles with L-conditioned problems like our valley function, which fx equal to x1 squared plus 100 times x2 squared. Notice how basic gradient descent zigzags slowly down the steep valley walls. This is due to the different curvature along different dimensions. And to overcome oscillation problems, we implement momentum gradient descent by accumulating past gradient with a decay factor, which we can see, well, here. The factor beta which equal to 0.9. Momentum builds velocity in consistent direction. This smooths out update and helps escape local minimum. In our valley problem, momentum significantly reduces the zigzag behavior and converges faster. And for even better performance, we implement the Adam optimizer, which is here. Adam combines momentum with adaptive learning rate per parameter. It maintains running ratio of both gradient and square gradients. Automatically adjusts step size, and notice how Adam navigates our pathological valley most effectively. This explains its popularity in deep learning application. And now let's see the result, which is here. Now our result clearly demonstrates the evolution from basic gradient descent to advanced method, where basic gradient descent shows oscillation and slow convergence issue. Momentum reduces oscillations, and Adam provides the most robust performance. This progression reveals how historical gradient accumulation and adaptive learning rate solve fundamental optimization challenges. And now for the application. This gradient descent Gradient power modern AI system. They train neural network by minimizing prediction error and optimize recommendation systems through latent feature learning and enable financial risk control via credit score module. And the principle we've demonstrated scale to massive real-world optimization problems. And for conclusion, through careful implementation and modification, we can overcome its limitation for practical applications. The journey from basic gradient descent to a dam shows how mathematical insights lead to increasingly effective optimization strategies. And that is all.